about that time for the second half of this session. I'll give people a minute or two to drift in because there's so many fun things going on out there. But while they drift in, I'll reiterate that that this is not the best way to learn or to teach DNS or DNSSEC. The better way to do this is hands-on. So after this session, go home and install some DNS servers. On GitHub, you'll find my DNSSEC labs. APNIC has some DNSSEC labs as well. Just set up the lab environment. If you get these slides from the Apricot program, they'll tell you how the lab exercises work, and just work through them and do the hands-on bits, because listening to me talk at you I cannot imagine anything less exciting to endure. Go and do this live. I might be very soothing, but it's a lot more fun if you type the queries and configure some servers and do it, and you're going to learn a lot more. So, feel free to listen to me, produce a continuous soothing drone of DNS information, but just go off and do the real world things. So we're now going into the second half of this presentation. I've skipped forwards. If you're following along in the songbook, I have skipped forwards about 100 or so slides. I've skipped over a lot of the basic DNS material because we simply don't have time for it. As part of that, I've also skipped over a lot of the operational details of how you set up DNS servers, how you set up resolvers, and a lot of operational details have been skipped. I'm just giving you edited highlights of the protocol. Please do go back and read through these slides and just do it in person. So before I can go into DNSSEC, I need to give a very quick crypto refresher, not too mathematical, and a very quick refresher on what is actually wrong with DNS to need DNSSEC. So I'll do the crypto refresher first because that's the order the slides are in, and then I'll talk about how the crypto gets put on top of the DNS and solves a bunch of issues. And hopefully, by the time we end the conference for the day, you will be comfortably numb and ready to just enjoy an evening off and good song. Yeah. So without further ado, cryptography is a way to encrypt or hash some content so that it cannot be read or intercepted by middlemen or by people who do not have the keys. There's different ways of doing crypto, and there's different reasons for doing crypto. All of those are out of scope. For the purposes of DNSSEC, the point of the cryptography is not to hide the message. We are not encrypting anything for the purpose of ensuring that nobody can read it without the key. We are using cryptography to assert that a certain amount of data have been produced by whoever owns that key or whoever is in control of the key. So what we're using cryptography for authentication and non-repudiation. We are not using cryptography for encryption. We're not using cryptography for hiding information from prying eyes. There's three cryptographic primitives that exists in the context of DNS. One is public and private keys. So asymmetric cryptography is one cryptographic concept that exists in the DNS. I'll talk a bit more about what that is in the next couple of slides. Another cryptographic primitive that comes into play in the DNS is message digests or checksums or hashes. Talk a bit more about those as well. And digital signatures. Those are the only three elements of cryptography you need to actually care about in DNSSEC. And you don't need to care about them very much. You need to be aware of their existence and roughly how they work. we are not going to play the fun little exercise where we do RSA by hand with very small numbers. The DNS cryptography is very abstract. It just exists, and we use cryptography in the DNS to authenticate or to assert the authenticity of the data in the DNS. A couple of words of vocabulary again, because the DNS standards use terms in certain ways that other places don't use. Most of the DNS documentation uses the word ciphertexts in contrast with plain texts to distinguish between the data as you can read it and the data as it's been processed through some cipher, through some encryption mechanism. Just a word. When you see ciphertext, just, you know, it's what's been through the crypto machine. A symmetric cipher is one secret key. So I have a secret, I share the secret with you and with you and with you and with you. As long as we all have the secrets, we can derive a given plain text from a given ciphertext. It's a two-way operation. I have a piece of data and I have a key, put both of these together, and I can read this, I can get the plain text from the ciphertext. So very simple and straightforward, but not how the DNS works. An asymmetric cipher is a little bit different. Instead of having one key, you have two keys, or rather you have a key and then you break it in half. You can encrypt with one half of the key and decrypt with the other half of the key. And it works in both directions. So anything you encrypt with the public half of the key, you can decrypt with the private half of the key. Anything you encrypt with the private half of the key, you can decrypt with the public half of the key. So it's commutative. You should decide which half of the key is public and which half is private, and not confuse the two. As long as you keep that in mind, an asymmetric system is a good way of allowing other people to encrypt for you and for you to assert that you have control over a key. Because if you encrypt something with your half of the key, only you can encrypt with some half of the key. So if someone decrypts and can read what you have just encrypted, they know that you encrypted it, because no one else can produce ciphertexts that decrypts with your public key. That's the fundamental principle that applies here. Is we use these asymmetric keys to prove that we are who we say we are. By encrypting something and by decrypting something and making it readable, we know that if we can read it, we know it has been encrypted by the other half of the key we have. And that's how DNSSEC works at heart. We'll see this in much more detail later, but it's one key, you break it in half of the key you keep to yourself. And by encrypting things with that key, and allowing other people to decrypt it with the other half of the key, you prove that you have your half of the key. And by proving you have your half of the key, you authenticate your data in the DNS. There's a bit more theory about that in this slide deck. You can go read through it, but for the purposes of today, all that matters is we use our half of the key to prove that we are who we say we are. Thirdly, a one-way hashing function is a mathematical function that takes a lot of data, compresses it, and spits out a fixed size number, regardless of how much data you pass through it. So you have an arbitrary amount of data, you run it through a little magic machine, and it spits out a number. The function has the amusing properties, or the interesting properties, that it's really difficult to predict what kind of texts will produce which number, and you can't work backwards from a number back to a text. So it's an easy way of representing an arbitrary amount of information as a simple string, a simple fixed size string of letters and numbers. There's different one-way hash functions. The ones that we use in the DNS are SHA-1 and SHA-2. Historically, we also used MD5 and SHA-1. If you encounter either of these anywhere, just stop using them. They're no longer secure. They're prone to collisions. So we've gone through these slides in some detail to expunge all records of insecure ciphers, but they still exist. Or the vast majority of use cases is going to be SHA-2 or a couple of more exotic EC ciphers, which if I give this tutorial again in a couple of months, I might change my mind and say you're going to see these EC ciphers and a bit of SHA-2. But there's a bunch of different functions. They do more or less the same. They just have different names, but their properties are the same. You feed it an arbitrary amount of text or data, and it spits out a number. You cannot work backwards from the number to the text, and you cannot predict which text leads to which number. So that's the 2 minutes overview of how hash functions work. So, an example of that is on this slide. You feed it the text, "This is a tutorial." You feed it through some hash function, and it'll give you a number. If you add one word DNSSEC to your plain text, you feed it to the same function, all of the number changes. So we've made a very simple change to the plain text, and it results in a very complicated change in the ciphertext. We make a rather more interesting change to the plain text. We run it through the function. It's completely different, but it's the same length. So you always get the same length of data out of your hash function. No matter how long the input is, the output is always the same length. That's an important function. A digital signature now is the combination of these two last concepts. You take your hash function, you take what comes out of your hash function, this bit, and you go and encrypt it with your key. If you can decrypt it with the other half of that key, you know that it has been encrypted with the first half of the key, and you can validate the data by feeding the same data through the same function. So given the same plain text and the same hash function, you will both end up with the same hash. If you then can decrypt the encrypted hash and come up with the hash you found, you know that it has been encrypted with the other half of the key. Does that make any sense at all? We'll let that sink in and repeat it slowly after I have a sip of water. So to do that again, so a digital signature combines the properties of a one-way hash with the properties of public and private key encryption. We use a hash function, a one-way function, a public function with no secrets at all. We feed a certain amount of data into this function, and we get this out of it. Anyone who feeds this text into this function will get this out of it. There are no secrets here. I do this on my laptop. You do this on your laptop, your laptop, your laptop. All of this information is public. Everyone can easily replicate this part of the equation. If you look at the data, which might be your A records, so your A records, you push it through this hash function, you get this out of it. If you look up the same A records, you run it through the same hash function, you get the same results. That's all public information. There's no secrets here. The only purpose of the hash function here is to turn the arbitrarily sized data that comes out of the DNS into a fixed size number of bits and bytes. So you might have a bunch of A records. You might have 4 or 5 A records under the same name. You hash all of those and you will get a fixed length string out of it. You hash a certain number of SOA records, you hash them, you will get a same size string out of it. The point of the hash function is to turn arbitrary length data into a fixed size string. We then use cryptography. We encrypt that fixed size string with our half, the private half of the key, to produce the ciphertext. Only we who are in control of the private key can produce this ciphertext. So out of that comes, out of that operation comes a bunch of gobbledygook, incomprehensible, but critical here is that only we can produce this. Anyone can produce this, we can produce this. Anyone else, given our public key, the other half of our key, can take the text on the right side of the slide and turn it back into this. Because if I have encrypted this with my private key, I will get this. If anyone else encrypts it with any other key, the result will be completely different. So if I decrypt this text and I come up with the same results, I know that A, it has not been tampered with, and B, I know that it was signed by whoever has the other half of the public key I have. That's the basic element that underpins the DNSSEC. We take data, we spit it into a machine that is completely public to produce a hash. We encrypt the hash with our private key, and we give everyone a copy of our public key. Everyone with a copy of our public key can decrypt our encrypted data and come up with the hash. They can then compare the hashes. If the hash is the same, they know two things. They know that the other half of this public key has signed this, and they know that what has been signed is the same, because the hash function, if you change even one bit in the input, the output will be completely different. The digital signature, if you encrypt the hash with a different key, the output of that will be completely different. So to work backwards and verify the signature, we decrypt this with public information. If we get the same results from the hash function, we know that the data have not been tampered with, and we know who signed it, right? So this slide basically says the same thing, but has a pretty little picture. So we take this is a DNSSEC tutorial. We throw it through our little hashing function. We encrypt using our private key. We decrypt it using the public key. And then we compare the hash that comes out of here with the hash we produced. If the string on the right side of the slide, if this and the one on the left side are the same, we know that this has not been tampered with, and we know that it has been signed using that private key. So that all we need. So all we need to validate any piece of information in the DNS is a public key, because all the other information we already have. We know the name of the hash function, because as we'll see, it's there. We know the data because it's what the DNS gives us. You ask for A records. Here are the A records. We can run these through the hash function. We get that string. That's all public. The public key, we'll see how we get it, but we get the public key from the DNS. We use those pieces of public information, and then we just compare the hashes. If the hashes check out, our data has been validated. It hasn't been tampered with. It's been signed. As I said earlier today, the data might still be nonsense, right? So the operator can still stick any nonsense in the DNS. If they sign that nonsense with their key, it's still nonsense. It's authenticated nonsense, but it's still nonsense. So the DNS is only as trustworthy as the operators. All DNSSEC can tell you is that this operator has signed this piece of data. So I will pause briefly for questions and let that sink in. Or heckling. This is a lot more fun with post-it notes and doing it in person in a workshop. But go through the slides and find the crypto lab and do that yourself to internalize this. It's a bit complicated, but if you break it down into simple steps, we have two pieces of public information and turn it to just verify the existing information. So with that out of the way, I'll now take a step back and say, why do we bother with this in the DNS? There's several issues with the DNS. All right, so it's a very simple protocol. It's UDP. There's no checksum. Well, with UDP on IPv4, there's no checksums anywhere. On IPv6, at least you've got a little bit, but data can be corrupted in transit. So adding a little bit of authentication allows you to verify that the data are at least somewhat cromulent when you receive them. There's no way to check the validity of DNS data at all. So there's any number of exploits. You can have bugs in your resolver. You can poison caches. The time to live is under the control of the DNS. So if you can modify the time to live, you can extend the desired lifetime of a record for longer than it exists and do replay things. There's a lot of things that can harm the DNS, and the harm can persist for a long time, because if you mangle the time to live, you have up to 32 bits worth of seconds that something can live and persist. So if someone can mess with your data close to your origin or before it hits a cache, the cache will spit out wrong data for up to the maximum TTL. There's mitigations you can do. You can clamp the maximum TTL, but at the end of the day, your cache will be lying for as long as the malicious party wants or specifies. There's other threats that affect the DNS. So within a set of DNS servers or clients, any part of the path can be compromised. Within the DNS servers of an organization, the zone transfers might be compromised. There's plenty of opportunities for things to go wrong. The DNS vulnerabilities are the gift that just keeps on giving. If you need an arbitrary vulnerability for an arbitrary example of a security problem, just go look at the DNS and you will find one. Everything is wrong with the DNS. It works, but it is full of wonderful ways to break. So here's a nice little diagram of everything that can go wrong with the DNS. Not all of this is interesting, so I'll talk through this a bit, but DNSSEC doesn't solve all of these. So DNSSEC solves some of these problems, but not all of these problems. Cache impersonation, DNSSEC can do some mitigation of. Corrupting data, DNSSEC can't help you with. If someone has control over your zone file, they can put any amount of nonsense in there and then sign it, and then it propagates, and it is now authenticated corrupt data. So if you have a vulnerability near the top of this diagram, if your primary name server before your DNSSEC pipeline is vulnerable, someone can put wrong data or corrupt data into your zone file. It will be signed, it will propagate down the system, and it can be DNSSEC validated. DNSSEC does not protect you from vulnerabilities in your infrastructure by itself. Other things that can go wrong is between your zone file and your primary server. If something is wrong in that path, things can go wrong. Cache pollution is something DNSSEC can fix, because if you validate the signatures, you can't tamper with the data before it enters in the cache, provided the caching resolver actually goes and validates the signatures, which we'll go into. Unauthorized updates are another fun one. If you have dynamically updating zones, if you put data into your primary server here and it signs it, if this update station is vulnerable, you are propagating authenticated wrong data. DNSSEC can't protect you from something wrong here. So if this is broken or this is broken, DNSSEC can't help you. Everything else, DNS can help you to a more or lesser extent. The next several slides are detailed explanations of all sorts of DNSSEC vulnerabilities. I could dwell on many of them, but I'm not going to go through all of them in tedious detail. Cache poisoning is the one I will go through a little bit because it's the main thing DNSSEC protects against. So cache poisoning is what happens when some attacker convinces the cache of some data that are wrong. So your resolver will go and ask the root servers and the authoritative servers for some answers, but instead of these guys answering, some attacker answers and fills the cache with wrong data. The attacker can poison the cache for leaf data like www.example.com, but the attacker can also poison the cache for upstream servers. So the cache can point com at different sets of NS servers, for instance, and then everything that you get underneath com will be suspect. So it's caches all the way down, and all the data are cached independently. So cache poisoning, if someone can put the wrong things into your cache, the cache will respond with these wrong things for not an indefinite amount of time, but for a certain length of time. So you want to protect your cache from serving wrong data. Does that make sense so far? So by making your resolver authenticate the data before it returns it to clients, you can protect against cache poisoning. The resolver will say, hey, I got records from the com zone which were not signed by the com zone operator. I'm not going to cache these. I'm certainly not going to return these to my clients. So the resolver goes and validates the chain of answers it gets as far up the tree as it can, and verifies that it's been put there by authorized operators. The resolver cannot judge that the data make sense or are good. It can be nonsense, but the resolver can assert that it was put there by the people who have control of the private key, and recursively validate this, which we'll see in a lot more detail later on. So cache poisoning is the main threat that DNSSEC protects against. And it's also the main threat to the DNS, because if you can poison the cache at any level, you can serve any amount of bogus data, which you can then use to, chain vulnerabilities to attack any other service. Other things, DNS amplification attacks, I'm really not going into this. It's where you use the very small, the property of a very small query to result in a lot of data coming out. DNSSEC, if nothing else, makes this worse, not better. Not going to dwell on it. Please read the slides. DNS hijacking is similar to cache poisoning. It's where you convince a recursor to go and query other servers for authoritative data. So it happens when your DNS has been modified by malware, for instance, or when a DNS server somewhere in the chain has been compromised or poisoned. Your DNS is hijacked and you are no longer talking to the machine you think you are talking to. So you resolve google.com, you get an A records, and it doesn't belong to Google, it belongs to someone else. So suddenly you are sharing your deepest secrets with someone else instead of sharing your deepest secrets with Google. Whether or not you wanted to share your deepest secret with Google, or that is up to you. But DNS hijacking is where you are convinced to talk to a machine that you did not intend to talk to. So that can have many implications, right? So if and not every protocol allows for checking that further up in the application stack. SSH will ask you, hey, this server, is that the one you think you're talking to? DNS can protect you, but a web server, plain HTTP, will not. If you are sent to the wrong server, you're just going to talk to it and share your hopes and dreams with it. These attacks don't exist in isolation. You can chain this with any other vulnerabilities to come up with hideously complicated but perfectly plausible and actionable attacks against many other parts of infrastructure. The DNS lives at the heart of the internet. If you are served wrong data, or if you are able to serve wrong data, rather, you can do a lot of harm. So DNSSEC allows you to protect against some of this harm. DNSSEC doesn't solve all the problems with the DNS. It certainly doesn't try to solve all of the problems on the internet, but it can make it a little bit more difficult to execute some kinds of attacks. Difficult, but not impossible. What DNSSEC cannot protect you from is denial of service attacks or amplification attacks. And if anything, as I said, it can make it worse. I'm not going to dwell on this because I simply do not have time. But DNSSEC does not solve amplification. It does not solve DDoS. There's things you can do to protect against those use cases. They're out of scope for today. And I'm just not going into that. I will go through this slide briefly because I must. Regardless of whether or not you deploy DNSSEC or do anything else I tell you to, or anyone else tells you to do, basic DNS security practices should always be followed. So you should always run the latest version of DNS software. Bind is well known for the vulnerability a week prize. It's been, it's a vulnerability every other week these days, but still, it's the gift that keeps giving. DNS servers break. DNS is a fiendishly simple protocol, which makes it fiendishly simple to make mistakes in it. And DNSSEC is, as we'll see, is simple-ish in concept, but the implementation is very tricky, and bugs will keep coming up. If you run a resolver or a recursive resolver, restrict queries to within your network, you should not allow arbitrary outside networks to use your resolver. That just, that's just opening the door to cache poisoning. Even if your validation works perfectly well, if there is a bug, they can still poison your cache. So defense in depth don't allow unauthorized clients or clients outside your network to query your resolvers. If I'm doing this workshop, I always advocate for people running DNS servers on their own laptop. Don't even trust your operator, just run it on your laptop, and the only client is localhost. Run your own validating resolver on your laptop and validates all the way to the end. But restrict queries as much as you can. If you have a name server in a network, just restrict it to that network. If you're an ISP, restrict it to your DHCP pools or your RA pools or whatever. Zone transfers, just prevent them. Didn't talk about zone transfers during this presentation, but only allow your secondary servers to transfer your zones. There's no need for other people to transfer your zones, not because there might be secrets in them, but because it's a lot of data. A zone transfer can be several hundreds of kilobytes to several megabytes of data, depending on how big your zone is. Why should that much traffic leave your network, especially given amplification attacks? If you're running binds or anything else, really run it with least privilege. That applies to any process anywhere in your network. Principle of least privilege. Randomized source ports, bind, unbound, everything does that by default. Secure the box, goes without saying. And then finally, once you've done the low-hanging fruits, so even if you don't get around to implementing, don't worry about DSIG, even if you don't get around to implementing DNSSEC, at least do the low-hanging fruits. It is not that difficult to update a DNS server. It's not that difficult to restrict queries. It's not that difficult to do any of the other things. Spend 5 minutes of your life to save yourself several hours of your life putting out fires. Do all of these things first. If you are running ancient software or if you are running an open resolver, just before you even think about doing DNSSEC, take a step back and fix those problems first. It will also be a lot easier to implement DNSSEC if you've done all the other things first. If you start out with a hideous pile of stuff, trying to add DNSSEC to it is not going to make your life any more fun. So with that said, I'm going to skip a whole lot of slides again because they do not matter in this particular instance. I'm just going to skip a whole lot of things. Unfortunately, I did not put in any bookmarks. Here we go. So with that out of the way, I'm now going to finally introduce DNSSEC. Unless there are any questions, let me pause for 1 minute. Okay, good. I hope everyone is comfortably numb. So DNSSEC is the pet name for the DNS security extensions. It's a whole bag of tools that have been piled on top of the DNS to protect the integrity of data in the DNS. And the way it does this is by establishing a chain of trusts. And this chain of trust is very similar in concept to the delegation tree we saw at the beginning of this presentation. So the chain of trust is walked in the same way as the DNS itself. For DNS to look something up in the DNS, you walk from the root downwards. Ask the root for com, ask com for Google, ask Google for www. Validation chain works exactly the same way, but backwards. So you check with Google if www is okay, you check with com if Google is okay, you check with the root if Google is okay, if com is okay rather. So it's a chain of trusts, and you can check each level as you walk up and down the tree. The way it's implemented is digitally signing the data, as we've seen in our crypto overview earlier. So we sign our records, we add little signatures, which anyone can go and verify to prove the integrity of the data and who signed it. So it's a bag of tools that uses a couple of simple concepts to achieve useful results. What DNSSEC signs specifically is we sign the record sets. So each individual record set, what we do is we add a signature to it. So the set of A records for a host, when you ask the DNS for A records, it will give you the A records for that given name. We add to the DNS something called an RR-SIG, which signs that RR set. So every records will have a signature paired with it. So if you have an A record, an NS records, and a start of authority record in your zone, you will have an RR-SIG for the A records, an RR-SIG for the NS records, and an RR-SIG for the A records. So each set of records has a signature. The whole zone is a collection of its data and the signatures of the data. And we build the chain of trust by publishing a new type of record called the DS records. If you look at the name of the DS records, it's similar to the NS records. The NS records points at the start of authority. The DS record points at the public key. So the chain of trust works in exactly the same way as the delegation chain. You put the records in the parent zone, pointing into the child zone. And this is done recursively, exactly the same as the regular DNS. So the root zone has a pointer to the com zone, the net zone, and everything under there. In addition to that record, it now also has a DS record. So we're not changing anything in the DNS with DNSSEC. We're just adding things to the DNS. This will become a lot more clear as I finally get to the picture bits, but I have to talk through the boring bits before I get to the fun bits. Fundamentally, to this part of the soothing drone is that we are adding things to the DNS. We're not changing anything to the DNS in principle. Normal DNS just keeps working. What we are doing is we're adding a little bit more information to the DNS to allow people to validate the data that are already there. So we take our data that exists, we go through it one step at a time, we add signatures, and we put the signatures in the DNS. We also put our public key in the DNS. So we're just putting everything, the whole problem moves into the DNS, and we can use the DNS itself to validate the data that are there. So what this does is it changes the model or the trust model of the DNS from one that is trusting and open to verifiable. So The DNS is still exactly the same, but now you can verify the data that's in there. We're adding verifiability to the DNS and not much more than that. And the way we achieve that is by adding these public key cryptography bits. Normally, DNSSEC doesn't actually add any more work. So the authoritative servers don't need to do more work for DNSSEC. Clients normally don't need to do more work for DNSSEC. The only servers that need to work a little bit harder for DNSSEC is the poor little recursive resolver that is sitting in the middle of all this. If you remember, I don't have bookmarks, but if you remember my pretty picture earlier, the little recursive resolver that sat in the middle was already doing a lot of work. It's just doing a little bit more work. The recursive resolver is just going to verify all this data as it goes through its recursive process. Again, there's no modifications to the core protocol. I will add that DNSSEC does rely on EDNS 0 working, so the packet sizes will get larger. So the rest of your network has to work for DNSSEC to work. If you've got 1980s or 1990s infrastructure with very small buffers, DNSSEC is going to make you fall back to TCP, and it's going to add a lot of latency. If you run a more or less modern network, your buffers will be large enough, and DNSSEC will work over UDP, and you don't have to worry about anything I just said. DNSSEC does not add any confidentiality. You still cannot hide anything in the DNS. The DNS is still a public directory of stuff. Anything you put into the DNS, anyone can query. DNSSEC does not sign the zone as such. DNSSEC signs individual records. So when during the workshop we say things like sign your zone, what we mean is sign all of the records inside your zone. DNSSEC signs every single record. Sorry. And the last point on this slide is important. The parent zone does not sign the child zone. So the COM zone does not sign anything underneath the COM zone. The net zone does not sign anything under the net zone. Trouble.is, trouble signs the trouble zone. IS does not sign the trouble.is zone. You're still delegating authority downwards. You're not giving more authority to your parent zone. You still have control over your data, and you have control over your keys. You're just giving people who query you the opportunity to verify your data. So how do we achieve all this? We add a whole bunch of things to the DNS. Earlier today, we spoke about A records, quad A records, NS records, etc. DNSSEC adds a whole bunch of them. So DNSSEC adds a new DNS key records, which is a public key. DNSSEC adds an RR-SIG records, which is a digital signature. It adds NSEC and NSEC3 records, which I'll talk about in excruciating detail a little later. And it adds the DS records, which I've mentioned earlier, which chains this all together, and it builds the branches of the tree, just like the NS records. It adds some packet options, which I'm not going to cover in this talk because we're not looking at packets. It adds a chain of trust, which I've talked about. And then the last three items, key generation, signing, validation, and key resolvers are just software phenomena. They don't really, they're part of the protocol, but they're just tools. All of this is added to the DNS. The DNS itself just works as it always has. We'll talk about these records in a bit of detail, actually, because we have to. Let me just quickly check my where my pictures are. So yes, so that's okay. Sorry, just get rid of that. Right. So the DNSSEC records we have is we've got this DNS key records. That's a new record that's been added to DNSSEC. And that's where you store your public key. So if you run the trouble.is zone, which is my zone, you add a new record to that zone with your public key. Here's your key, and anyone can get that key out of the DNS and can use it to verify all the signatures in that zone. The signatures themselves are stored in these RR-SIG records. So for each record you have, you'll have a signature record, right? So you have an A record, you have a matching RRSig record. You have an MX record, you have a matching RRSig record. You have a text record, you have a matching signature. So for every record you have, you add a signature. The good news is you're not making these signatures manually, right? So this all of this is software. You are not going through in your zone file by hand and recalculating the signature for every time you change your IP address. You're not going through by hand on a piece of paper, calculating the hash, copying the hash into your text file and serving it. Software will do that for you. The DNS protocol just adds these things. As an operator, you do not have to care much about any of this because the software does it for you. But conceptually, you need to know they exist to debug. So for every record you add to your zone file as it exists in plain text, software will add a signature. Every time you change your A record, the software will go and fix the signature for you. NSEC records are a bit special. They fill in the gaps between the things that exist and cover the things that don't exist. So one thing that always breaks people's minds when I teach DNSSEC is the concept of denial of existence. You cannot prove the non-existence of a thing. It's mathematically impossible. You cannot prove that something does not exist. It is a lot easier to prove the things that exist. And by excluding those, you have the things that don't exist. You cannot enumerate all non-existent things because there's an infinite number of things that don't exist. All you know is the things that exist. You don't know all the things that don't exist. What the NSEC records do is they fill in the gaps. So for everything that exists, between all the things that exist, NSEC records fill that gap and say everything between here and here does not exist. Right. So you have, imagine a dictionary of words. You know, you have the first word with an A and then the second word with an A. You would see an NSEC record between those two saying, between this word and this word, there are no words. Or between here and here, nothing exists. The reason we have this is because, you know, you could manufacture a record with a signature pretending that something exists that doesn't. You do not have a web server today. Your organization does not have a www.example.com. Someone could manufacture a www.example.com A record and serve it to anyone querying you, you know, man in the middle. You answer www.example.com. Oh, here it is. Go there. Your organization doesn't have a web server today. Tomorrow, your organization wants to set up a web server. But suddenly, everyone already knows that you have a web server pointing at someone else. The NSEC records allows you to state that there is no web server. This machine does not exist. You might not have IPv6 today, so you might have an A record for your mail server, but you don't have a quad A record for your mail server. The NSEC record allows you to say there is no quad A records, because otherwise someone else could add a quad A records for your A record. So anyone trying to go to your mail server over IPv6 will instead end up with an attacker's mail server over IPv6 and send them their passwords and their hopes and dreams. And you don't want this. So NSEC records allow you, the operator, to say this does not exist without having to go through the mathematically impossible process of identifying all the things in the world that don't exist, because, you know, you'd never finish. NSEC, always fun. DS records. The DS record is analogous to the NS records. The DS record builds the chain of validation, just like the NS record builds the delegation chain. The NS records you put in your parent zone to say, go and look there for that child zone. Go and look there for everything underneath here. Example.com, go and look at that server for everything under example.com. The DS records is the same thing. It says the public key of this, the hash of the public key of this child zone is this. We'll look at an example in a moment, and I'll do that in a terminal. It allows you to validate the the signatures by walking a tree. So the DS records build a chain just like the NS records build a chain. NSEC 3, I'm not going to talk about. NSEC 3 param, I'm not going to talk about, except to say that they are better NSECs. So NSEC has some interesting drawbacks, which I could talk about for hours. NSEC 3 mitigates them. NSEC 3 param helps mitigate them. So back to the operational parts of apricots, you are operators. You do not have to worry about all of these things in tedious, excruciating detail. You are not expected to write down DNS key records on pieces of paper and copy them into files. You are not expected to generate RRSig records by hand. You will never, ever make an NSEC record in isolation. None of this is done by humans. All of this is done by software. The only reason I'm tediously droning on about these things is that all software sucks and the internet sucks more and things go wrong and then you need to debug it. If you understand the concepts, it's a lot easier to debug the problems than if you consider everything opaque. So, reassuring thoughts, you don't have to do any of this manually. The software will do it for you. But to use the software effectively, you need to understand at least a little bit about how this stuff works. So practically speaking, what do we add to the DNS when we start signing things? Not very much, it turns out. So we add a DNS key to every zone. So the trouble.is zone will have a DNS key in addition to its start of authority records, any NS records, and anything else I might have at that level of the tree. Google.com zone, it will have a DNS key added to its zone. So that's one extra record you add. It's a very large record. You add it to your zone. Also added to every zone is one or more NSEC records. So between the things that exist, software will add NSEC records to fill in the gaps between the things that don't exist. Software will also add RRSig records for every RR and one or more DS, so a delegation signer record for every delegation in your zone. That's the only thing that gets added. So RRSigs, I've been lying to you. I've been saying it gets added to every record. That's not strictly true, but for the purpose of today's presentation, don't worry about that. So the way DNSSEC works in practice is that people who run authoritative servers and write zone files and say this server lives there and this name has that address or this address has this name, what these people do is, in addition to writing their zone files, they also sign these zone files. Signing these zone files means they configure their DNS server to sign their zone files. When I started teaching DNSSEC a long time ago, it was a tedious process where you had to run commands to go sign your zone. That is no longer the case. What signing their zones means in practice in 2023 is it means they turn on DNSSEC. So they enable an option. Done. Authoritative servers will also reply to queries just as they always had, but they also include a signature. So if you ask a question of a DNSSEC enabled authoritative server, when you ask for an A record, you will also get a signature for free with that A record. So if you ask the DNS server, hey, give me the A records for the zone, and by the way, I speak DNSSEC, the server will say, here's the A records, and by the way, here's the signature. And you get the signature for free. And you can then go and validate it. So you don't have to worry about it. You're not doing this manually. Your server does it for you. But the way the protocol changes is that in addition to giving you the A records, it's also giving you the signature of the A records. So every query, every response to every query, the DNS will include the signature, which allows you to then go and validate it. So that's the authoritative side of the story. So a bunch of things are added to the zone, and every query, we include a signature. The resolvers, the recursors, they need to actually do more work. So the recursors go and authenticate the responses they get from the server by walking these DS records and by verifying these RRSigs with these DNS keys. So the resolvers need to do a bit more work. And the way they secure the end user at the end of the day, which I haven't forgotten about the end user, is that if the data ends up being bogus, the resolver will say serve fail rather than giving bogus answers. So if anything goes wrong in the validation of these data that are in the DNS, if the DNSSEC validation fails, the recursive resolver will say fail. So, the user will see it doesn't work. So, the error handling part of DNSSEC isn't particularly user-friendly, but it does achieve the goal we want. So instead of giving you the wrong mail server, or instead of giving you a quad A records for a mail server that does not exist, or a web server with a long time to live where no web server exists, the validating resolver will just say, no, I have no answer to this question because I could not validate this answer. So it will go through the tedious process of resolving your query. Hey, resolver, give me www.example.com. The resolver will go through and do all these queries from the root down to get the answer. And then it will also do all the tedious processing, working its way back upwards, verifying that the signatures exist and check out. If that goes wrong, the recursor will say, no, I couldn't validate it. We are done here. So that's what's added to the resolver. EDNS 0, not going to talk about. Opt, not going to talk about. Flags, not going to talk about. Not going to talk about. Not going to talk about. Right. So let's talk a little bit more about this DNS key records so that it doesn't scare you when you see it in the wild when later on I actually do this. A DNS key record is this public key. So it's half of your key. You keep your private key to yourself. You stick your public key in the DNS. And it's a DNS record just like any other DNS record, right? It's just long and it contains a whole bunch of stuff, but it's just a DNS record. There's no new magic here. It's just a kind of record that you stick in the DNS. Just like any other record, it's got a label, example.com. It's got the 3600, it's got a time to live, just like any other record you stick in the DNS. It's got a name, it's got a time to live. The type is a DNS key, and then it's got a whole bunch of flags and other things, which I'm not going into now. And then it's got the key itself. That's it. And it's got a little identifier that's derived from the key. So you, as an operator of a zone, you stick your public key into your zone. You say, this is my public key. If you want to validate records signed with this key, here is the key. This is all you need to go and validate this signature. Nothing magic there. A signature then also is a normal DNS record, just like an A record. It's an ordinary DNS record. It's got a name and it's got a whole bunch of stuff in it. So the example I've got on the screen here is a signature for an NS record. How do I know it's a signature for an NS record? Because it tells me. It tells me that it's a signature, it's an RR-SIG, and it tells me what it is signing. So it tells me that I am signing an NS records. And then it tells me a bunch of other things. I have been signed with this algorithm. I have been signed, I'm signing this many things. It's telling you, it is giving you the information you need to validate this signature. And at the end of the record is the actual signature. So the signature at the bottom there, together with all the flags and other bits, allows you to validate that the NS record rather you got is the one that the owner of the private key put there. Right? Does that make sense? So you take this signature at the bottom there. So all of this stuff. You take all of this. You take everything you got from the NS records, you use all of the other bits of fluff that appear around this records, and if you get the same hash out here, then you know that this NS record has not been tampered with. So if you take the NS records and you take a hash, if you decrypt this string here, if you decrypt this with the public key, you'll get a hash. If you take the NS records, run it through the same hash function, if those two are the same, your data have not been tampered with. So it's all public and it's all just DNS records. All of this is just metadata. All of this is just telling the resolver, here, this is what you need to validate this signature. But at the end of the day, from an operational perspective, it is just DNS. There is nothing to be afraid of. It's just a bunch of data that we've pushed into the DNS, right? And we've not changed the protocol in any way. So these records are queried just like any other record, except that the RRSig record is given to you for free with every other record you query. So if you query an NS record, you will get the signature for free. You don't have to do a separate query, so that would be wasteful. You get it for free. You ask me for a name server, here's the name server, and here's its signature. And then you can go and validate this. Also, the signature is cached, right? So it's 3600 here. It has a lifetime. You can be sure that this signature is valid for the next this long. And that is in lockstep with the data itself. Interestingly, though, this signature is only valid for a certain window of real time. And we'll get to that in a little moment, but these two numbers are what make DNSSEC difficult and fiddly. The signature is only valid for a certain window of time. Come to that later. NSEC records, not going to go through in detail, but again, it also looks just like any other DNS record. It just has a lot of data, incremental gobbledygook at the bottom of it, but it's just another DNS record, just like any other DNS records. Not going to talk about how DNSSEC or NSEC works. We talked about that. It would make this much too long. So skipping forward a bit to the fun bits, to the DS records. So the DS records as an operator, this is the one you actually care about most. Everything else is done by software. So if you sign your zone, the DNS key gets into your zone by itself. The RRSIGs get into your zone by themselves. The NSEC get in there by themselves. You don't have to worry about it. Your software does that all for you. No operator intervention required. You've just been listening to Philip drone on about it to help you debug it when it fails. The DS records actually requires operator intervention at some point. So once you have signed your zone, once you have added a public key and you have added your RR6 records to your zone, somehow you need to build that chain of trust. So somehow you need to be able to tell people that, hey, my public key is this, and they need to be able to trust that. And the way you do that is you take the hash of your public key, so your DNS key record of your public key, you take a hash of that and you stick that hash in your parent zone. So you tell, in my case, the IS zone, that the hash of the public key of the trouble.is zone is this. And that allows anyone who wants to validate anything in the trouble zone to go up and ask the IS zone for, is this key right? So you build your chain that way by checking that the hash of the public key matches the parent zone. In the parent zone, we'll have the same thing. You chain your DS records all the way to the dot zone, to the root zone, where there's a well-known DS records that everyone has, just like the root zone has a well-known NS records that everyone has. Everyone has the a2m.rootservers.net. Those are well-known information. Everyone has the root key signing key. That is well-known information. If you have the IP address of one root server, you can bootstrap the entire DNS resolving algorithm. If you have the public key of the root zone, you can bootstrap the entire validation chain. So DNS server implementations now have one more piece of information. They have the DS record of the root zone baked in. And we could have a spirited discussion about rolling that key, but not today. So does that roughly make sense to now? I see a lot of confusion and I've been droning a lot. I think we're almost coming up to the fun bit. DS record, right? It looks just like another DNS record. Again, I'll keep repeating that. There's nothing magic about DNSSEC. What we do is we add a DS record into our parent zone with the hash of the public key of our child zone. And that builds a chain. And the parent zone will have its DS record in its parent zone, and that one will have it in its parent zone, and so on and so forth. Everyone is in control of their own data. That has not changed. Everyone signs their own zones. That does not change. You just, you delegate the validation by putting the hash of your public key in your parent zone. So just as with delegation, you put the NS record of your zone in your parent zone. With DNSSEC, you put the DS record of your public key in your parent zone. DS record is a pointer to a public key. NS records is a pointer to a start of authority records. I'll show this in a terminal in a moment rather than droning on. Of course, for all of this to work, the DS record also has to be signed, right? But this lives in the parent zone, so the parent will sign the DS records. So trouble.is, my DS record lives in the IS zone. The people who run IS are going to sign this DS record. And then you will need to validate that with the public key of the DS zone, not my public key, because not my zone, but with the parent key, and on and on and on upwards. Secure and insecure delegations. DNSSEC is an additive process. We cannot expect everyone on the internet to sign their zones, clearly, because I'm still doing this in 2023. If you do not have a DS records, DNS just keeps working. You just cannot validate anything below there. So if you have an NS records pointing at something and no matching DS records, everything underneath there is an insecure delegation. It will still resolve. You just can't validate it. For the longest time, the DNS was completely impossible to validate because there was no DS records in the root zone. That's been fixed a long time ago. Most TLDs also have, or most or many, or plurality, pick a word there, will also have DS records already. I don't know, is PH signed? Does anyone know? So, someone check if PH is signed. Many CCTLDs and TLDs are signed, so you can build your chain of trust completely. If there is no DS records, the chain of trust breaks and you cannot validate. So you can resolve, but you can't say authoritatively whether the data are good or not. So there's a difference between an insecure delegation and a broken validation. So if the chain of trust is intact, but the signatures don't validate, that means something has been tampered with. If there is a DS record missing somewhere, it doesn't mean anything has been tampered with. It just means you cannot validate end to end. And that's not necessarily a problem. It's just the DNS falls back to regular DNS. I'm sure there are questions. And before I get to the next bit, I must drink some water. This is enough. The good news is you've only got 20 more minutes of me. All right. Let's get into one more bit of abstraction and then show a quick demo and then get out of here. 3 hours is both not enough and way too much, right? So far I've been talking about keys, and there's one key and there's a zone key, and that's the only key, and private key and public key, and not much more than that. For many reasons, DNS adds one more layer of indirection in the validation chain and in the in this key chain of public keys that can be validated. It makes a distinction between a zone signing key and a key signing key. instead of signing your zone with your one key, we have a separate key for every zone called a zone signing key. And we have a key signing key that signs your zone signing keys. This allows for many operational advantages, none of which I have time to cover. But the existence of this phenomenon is important to understand the demo. What is in the DS records is the hash of the key signing key, not the hash of the zone signing key. The zone signing key is within a zone, so every zone can be validated completely in isolation. So if you have a signed copy of the trouble.is zone, you can validate it completely in isolation. You have the public key of the zone, you have each records, you can validate it without doing any other work. The key signing key is added as an abstraction for the delegation signer. So the trouble.is zone has two keys. It has the zone signing keys, which signs all the records in that zone, and it has a key signing key, which only signs the zone signing key. And the DS record points at the key signing key. So it's still a chain. It's just there's one little link in that chain, which I've not told you about. I haven't been lying. I've just not told you about that little link in the chain. There's one more key in the process that needs to be validated. The reason for that key, I'm not going to go into today because it would make this presentation 4 times longer. But when I go through this demo next, just remember that there's one level of indirection. There's a key signing key that signs the zone signing key. Right, so I think I'm going to stop doing slides for a moment and just do validation by hand, because that's always fun to do in practice. And we've only got about 20 minutes left, so we should be able to manage it. So let me pull up a terminal window here. That's always fun. This would be a lot easier if I did not also have to hold a microphone, but that's all right. Let me share this screen. It's all right. Don't worry, I will give you this. There we go. Is this roughly large enough? I think it is large enough. Oh, hello. No feedback. Let's not play that game. Let's not break anything. Song requests. All right, so I have, for my sins, I have a domain. First of all, I should check if DNSSEC actually works in this network. I will assume that it doesn't, so I will log into a machine where I know that DNSSEC actually works, because otherwise I will confuse myself and you halfway through this demo. Let me go to a machine where I know that DNSSEC works. There we go. Come on. All right. So let me ask my my local DNS server. Let's just do something simple and ask for trouble.is. Right. That is me. This is hopefully fairly familiar outputs to everyone who's used DNS. So I use drill. Other people use dig. Use whatever strikes your fancy. It's up to you. You have a whole bunch of flags here, which we're not going to worry about too much. The thing we worry about is this. We have trouble.is, we have a time to live, we've got an A records, and that's just where it lives. This is a normal DNS query. There's nothing DNSSEC here. My zone is signed, I promise, but if you just do an ordinary DNS query, you wouldn't know. If we tell drill to please, give me some more DNSSEC information, drill is going to do that. Let me make this window a little bit wider. The -D flag to drill says, please go and do some DNSSEC. Just enable DNSSEC, do all the validation goodness, and tell me how you have done it. If you compare the flags here with the flags here, you will notice that there's one more. So here we have a flag that says it's the response to a query. It was a recursive query, and recursion actually happens. If we go here, we've still got those bits. So it's still the response to a query. Recursion was desired, recursion was available. And by the way, you have authenticated data. So this little flag, the AD bit, says that my validating resolver has managed to confirm by walking this chain of keys, which I've been ranting about for the last hour and a bit, that this is legit. This data have not been tampered with. So we get the same answer. So we get the same A record out, but for free, at no cost to us, no electrons were harmed. We also get a signature together with our A records. And this signature says the time to live of the signature is the same as the time to live of the results. It says, hi, I am a signature. I am a signature of an A records. I have used these magic things to produce my signature. This signature signs an A records with a time to live of 3,600 seconds. So the original time to live of this records, regardless of any caching or anything that happened in between, is 3,600 seconds. The time to live, as I see it here, is a little less because my cache, I've answered this question before, my cache is going to keep this time to live decrementing. It's not going to ask anyone else anymore. This 3,600 is here because that's the original time to live of this record before any caching happens. This key is valid within, or the signature rather is valid within this window. More on that later. This signature, this RRSig record, has been signed with this key ID. This is the ID, the magic number, the name of the key that has signed this zone, or this record rather, is this. You can go find this particular key by asking for it in the trouble.is zone. So this record this signature record says, I have been signed with this key, which you can find here. If you go and find this key there, and you put this information with that key found in this zone through the machinery of validation, you will come up with whatever this decrypts to. Right? Does that make sense? So what the resolver is going to do is, first of all, it is going to download the DNS key with this ID from here. How does it do that? It just goes and asks for it, right? So it goes and asks a DNS key records. Dear DNS machinery in the sky, please give me the DNS key records that belong to the trouble.is zone. Why do I ask these? Because I've been told to get them there. So well, do exactly that. I get a whole bunch of stuff. I get 1, 2, 3 keys, right? Everyone agrees? 3 keys. I also get a signature for free. Why do I get this? Why do I get this signature? Because I asked for it. If I turn off DNSSEC validation, I can still go and ask for DNS key records, but I don't get the signature for free. And the authenticated data flag disappears. So I'm going to ask for with it. So I get a bunch of keys and I get a signature covering the keys. So it's recursion all the way down. But let's ignore this bit for the time being and go back to my trouble.is A record first. Let's go back here, wherever it was. Here it is. We are only interested in one specific key. We are interested in this key here. So the 43534 key is the one we're interested in. So let's look at our DNS key records. Is it this one? No, it's not that one. Is it that one? Nope, it's not that one. It's this one. So this key here, this public key is what we need to decrypt this signature. So the crypto machinery in my resolver is going to take this key and this gobbledygook And these 2 bits of metadata, it's going to plug these into a little machine, and it's going to come up with a hash. So decrypt this with the key I saw earlier, decrypt all that, you come up with a hash. Which hash do you come up with? You come up with the hash of this. So if I calculate the hash of this, I decrypt this, if those 2 numbers are the same, that has not been tampered with, right? Agree? So far, so good. But how do I know that this public key has not been tampered with, right? So we downloaded, we've been told here that to validate this record, here's the signature. To validate this record, go and download that public key from there, decrypt this with that public key and compare the hashes. How do you know that whichever one it is, this one, how do you know that this public key has not been tampered with? In exactly the same way, you look at this signature and we go through the same tedious process again. This signature, hello, I'm an RR signature for a DNS key records with a bunch of fluff, valid for a bunch of fluff, made with this key, which you can find in a trouble.is zone, which encrypts to this. So to validate that this DNS key has not been tampered with, we need to go and download this key from the trouble.is zone. Conveniently, it is right here. It's that key, right? So this key, it's contained in my zone. This is the key signing key. So that's the level of indirection I told you about a couple of minutes ago. This is a little bit that chains it all together. The algorithm is exactly the same. We do exactly the same thing we did earlier. We go and decrypt this with that. We check that that matches the hash of this. If it does, it has not been tampered with. Everything is great, sunshine's rainbow, and we are all happy and everything is still intact. But how do we know that this has not been tampered with or that this has not been tampered with, right? We need to go and look at this key here, this DNS key here. How do we know that this is actually the key signing key of the trouble.is zone? We need to go and ask the IS zone for the DS record pointing inwards. So we go and ask trouble.is DS. So that's where the validation chain comes in. We've now validated the trouble.is zone internally, but we don't know that whoever signed this zone is actually the person who this zone has been delegated to. So internally validated, it's all okay. The signatures check out, no problem. It's all good. But we don't know that it's actually been signed by the operator of the trouble.is zone. To get that, we need to get the DS record from the IS zone, which the operator has put there. So we go and ask the DNS, give me the DS records of trouble.is. The DS record of trouble.is says, hi, the trouble.is key signing key has this ID and the hash of that public key is this. So this says, this magic number is the hash of 21683 magic number. This says that's the hash of this. So whoever has put that DS records into the IS zone has said the key signing key of trouble.is has this hash. Fine, fair enough. How do I know the IS zone has not lied to me? Are we starting to see a pattern here? Right, so together with my DS records, the IS zone has helpfully given me a signature. This signature says that DS records you saw earlier has been signed with this key, which you can find in the IS zone. How do we get this record? We go and ask the IS zone for DNS key records. right? We just keep doing this until we run out of time, or we realize that actually software is a lot better at this than humans. So we do this, and we go, okay, this signature has been made with key this, which you get in the IS zone. So let's go and look. 29625. 29625 is, which one is it? It is this one, right? It's a longer key, different algorithm, but same principle. We get this key, so we use this key to decrypt this, which will tell us the hash of this, which will eventually let us validate this. So it's turtles all the way down. We just keep validating signatures all the way up the tree until we run out of signatures to validate. So IS zone, we've now got the this one, which is a zone signing key of the IS zone. We can, how do we validate that this record has not been tampered with? Well, this has also been signed. Somewhere is a signature. Here's a signature. There's two signatures, don't worry about that. We have a signature for this record. We go and validate that this key has not been tampered with. And then, the process continues all the way up to how do we know that the root has been signed and not been tampered with? Well, we know because that DS records is known to us. That's a well-known record, just like the addresses of A through M.rootservers.net. Now I can, tediously keep going through this key by key by key until we're all numb, but I've got 4 minutes left. So that's not going to get us anywhere. So let me end this with a nice graphical representation of how this works. Share the right screen in a moment. Come on, the correct screen. Here we go. I will do update now. Stop share, start share, and it is that one. So there's a fun little service on the internet which does all that tedious process. Well, all that tedious processing is done for you by your DNS servers, of course. You never have to do this manually. But if you want to debug DNSSEC, you can do what I've just done and tediously walk that chain by hand, which is not fun for anyone. Or you can use this fun DNS Viz tool. There's a pointer to this at the end of that slide deck, which will do exactly what I have just been doing by hand. So it sees the A records for trouble.is, and it tells you it has been signed by some DNS key. Which ID was it? This 43534 key. This key has been signed by that key. This DS record points at this DNS key. This DS record in turn has been signed by this key. This key has been signed by that key. The hash of that key is this DS records, which has been signed by that key, which has been signed by that key. And then we're at the top of the tree. So it's fiendishly simple in principle. It's just a chain of validating signatures all the way down. And that, in a nutshell, is DNSSEC. And the remaining 3 minutes of this talk, I will fill by saying, just go off and sign your zones and don't be afraid of it. But again, I've said it at least a dozen times. There's 260 slides in the slide deck on the Apricot program. Get them, read them through in your own time, and then set up some DNS servers in a lab and just play with this yourself. The only way to understand this properly is to actually just do it. So either you can just sign your zone and be happy until it breaks, or you can sign your zone and then poke around at it, throw some queries at it, and just look at some keys and until it makes sense in your head. Just keep doing that until you see, oh yes, this is how it works. There will still be edge cases, and I'm so glad Anurag is not in the room to come up with an edge case. There's still a lot of fun edge cases in DNSSEC, where you go. So I've been teaching DNSSEC for, I don't know, the example was from 2009. I think that's probably when I started teaching DNSSEC, maybe a bit earlier than that. I still have to think about some things sometimes with how did this happen? And tediously go through it, but it becomes easier to debug problems if you start from the smallest piece of abstraction, start from the records, start from the key, and work your way up, look at some packet captures, and understand the protocol rather than just blindly turning it on in your DNS server and hoping for the best. And on that cheerful note, I have carefully not left any time for questions. Thank you very much. I hope this was fun. You want a question? Okay.
Fine. Look, not a question, just a comment to anybody who want to do this. Yeah, be registered with GoDaddy, our top level domain. It is very hard to find the place where to add the DS record. They're always trying to steer you something paid program for that. Keep looking for it. There is a place where you can add a DS record for free. You just need to find it. They really hide that very well. Sorry.
No worries. All right. Yes. I think that is all for today. That was enough. Oh, hi. Sorry. Take it easy, or use that one. Use this one or that. I'm gasping.
Thank
for
you.
beer.
Yeah, I've heard about DNS over HTTPS. Is it better than this, or is this DNSSEC gonna be still in the place?
They are completely different things. They have nothing to do with each other. So DNS over HTTPS is unrelated to DNSSEC. It's one is an apple and one is an orange. They're different things. DNS over HTTPS is replacing UDP with HTTP on the transport layer. You still have DNSSEC inside your DNS over HTTPS.
DNS over HTTPS is for end user privacy, whereas DNSSEC is help us in preventing the DNS hijack.
Yeah. So yeah, DNSSEC only provides integrity. DNS over HTTPS adds privacy, maybe, under some limited circumstances, in good lights, sometimes, aspirationally, when it works, if it works. But other than that, it's really nice. All right. With that out of the way, I think it's time for a social event. One more? Oh, that's fun. So yeah, if you have any, it's not me abusing it. I've done enough abuse. If you have any questions, just email me. Look through the slide deck. I can easily be convinced to come and teach DNSSEC for days at a time. Make me do it. Just give me more than 3 hours. I dismiss you. Hello. Yeah. How you want to do a buff? Good luck with that. Hello, Gara. Good of you to pop in at the last moment.
Sorry, actually, I want to attend this session, but
That's all right. Good to see you again.
basically, we are working on public awareness for our community. So basically, with the aim of providing them protection from cyber threats.
Good stuff.
Maybe I will be in touch with you.
Of course, yeah, you know where to find me. You had one of my Atlas probes, I think, don't you?
Yeah,
You're one of the few Atlas probes which still run. Everyone has abandoned my one. You're the last one to probe still.
And then you want to go up there?
It's just us.
It's just us.
It's cozy.
Yeah, it's cozy. So, start. Hello, good afternoon, everyone. Yes, that's mic. I sound great here. So, so hello and good afternoon, everyone. It's like 10 minutes, 15 minutes past 6, but we're going to start now for our DNS abuse roundtable discussion. So as of the moment, by the way, I am Aris and I'm the moderator for this particular session. Yeah, and I am the vice chair for Apralo, and it is an ALS, no, sorry, it's an RALO, and it's part of the ICANN sphere. And I think Save would agree with that. And currently we are joined by a couple of experts and also some people who would be mentioning some things that are related to DNS and also not only that, but technology in particular. So moving forward, I would like to first introduce our respective speakers. Then after these speakers have given their specific talks, we would be opening the floor to everyone who wants to ask questions, and not only ask questions, but also maybe provide details, or maybe you could give some suggestions or insights about our topic for today. And we could also give our takes on that, and we could discuss so that we could, as much as possible, come up with an output that would be beneficial for all of us and all of actually we are stream live. I was mentioned earlier to me. So, so we're live. So anyone out there who is currently watching us, hello. Okay. So our first speaker for today is the Stakeholder Engagement Manager for the Asia Pacific of the Internet Corporation of Assigned Names and Numbers, or simply ICANN. And she's currently a Stakeholder Engagement Manager, which I mentioned. And actually, she engages with the community within APAC and facilitates the participation of the ICANN multi-stakeholder internet governance discussions. She joined ICANN last May 2016, and prior to her current role, she was with the ICANN contractual compliance team. So she graduated with an honors degree in economics from the National University in Singapore, and is a CSEP1, which is a Certified Compliance and Ethics Professional International Certified. So as CSEP-I. Yes, I stand corrected. So to start things off, this is with regards to the introduction of ICANN. So you would be more knowledgeable on what ICANN does and what ICANN is. So may I call on our first speaker, Ms. Yanjin Tan.
Thanks, Aris. You make it sound like a talk show, but I'm going to try to make this interesting. But anyway, I'm Yanchin. So as mentioned by Aris, I'm the Stakeholder Engagement Manager from ICANN. But before I start giving an introduction to ICANN, I'm just in this room, has anyone not heard of ICANN before? Just show of hands. It's okay. You haven't heard of ICANN before. So I guess, I actually don't need to do this introduction. Everyone knows ICANN. Okay, I'll try and give a quick overview, especially for people maybe who join us online or on YouTube Live if they're newcomers. So I'll share a little bit on introduction to ICANN. Okay, so before I talk about what is ICANN and ICANN's role, I would like to talk about a quick overview on how the internet works. So basically any device that connects to the internet has a unique IP address, internet protocol address. This address works like postal addresses. So it provides the information to basically send content and data to the correct recipient. But the problem is if we want to remember IP addresses for human brains, it's quite impossible because it's a string of number or alphanumeric. So instead we use domain names. So for instance, example.com. And these domain names will convert, will basically direct to the corresponding unique IP addresses so that the correct content and data will be sent to the correct recipient. And so basically, this is how the internet works. And we have three, because of these unique identifiers, the internet works. And these are managed or coordinated by different organizations within the internet governance ecosystem. And as a summary, we have three main unique identifiers. So we have the internet protocols. This is the common language used by the devices so that they can communicate. And the internet protocol standards are defined within the IETF, Internet Engineering Task Force. And then we have the second unique identifier, which is IP addresses. This is managed by regional internet registries. So in the AP region, it will be APNIC, which they're having their meeting as part of this Apricot conference as well. And then, of course, the third unique identifier would be domain names, and this is coordinated by ICANN. So this brings me to my initial question on what is ICANN. We are the technical coordination body for the domain name system, the DNS, and we ensure the stability, security, and interoperability of the internet. So going on to ICANN ecosystem, the ICANN ecosystem is made up of three parts. We have the community, which you are a part of. The community really is a global multi-stakeholder community of volunteers coming from different stakeholder groups. So we have internet users, governments, civil society, technical community, and others. And then we have the ICANN board. I'm sorry, so just backtrack a little bit on the community. The community basically comes together to discuss and develop policies that are related to the DNS. And then the ICANN board, which includes global representatives from the community, they would review and adopt these policies that are developed by the community. And then basically the ICANN board will direct the ICANN org, which includes ICANN staff, to implement adopted policies. And on multi-stakeholder model, so to reiterate, the ICANN multi-stakeholder community comes together at ICANN, and through a bottom-up consensus-driven policy-making approach, each individual and stakeholder group plays an important role in developing policies that impact the DNS. So in terms of formal structure, we have three supporting organizations, which you see in this slide on the left. Supporting organizations developed policies based on their representation. And then on the right side, you'll see 4 advisory committees. These ACs do not develop policies, but they do provide input based on their representation, and they can participate in the policymaking process as well. So for instance, at large, because we're talking about AP Radio today, so I'm going to just zoom in a little bit on at large. So at large advisory committee, the ALAC, provide voices and input from internet users. And then there are over hundreds of ALSs, so as Aris mentioned, at large structures, and also a growing number of individual members. So all of this, they are organized by regional organizations, and AP Radio, which is for the Asia Pacific region, is one of the 5 regional organizations that sit within the ALAC. And so just quickly going back to our key topic here, which is DNS abuse. I mentioned that part of ICANN's mission is to ensure the security and stability of the DNS. And with rising cybersecurity issues, DNS abuse has been a hot topic discussed among the community for the past few years. Many efforts and initiatives have been taken within the community and with ICANN.org as well to mitigate DNS abuse or security threats. And later, my colleague Champika will share more details on those. But before I end, I would also like to pass it back to Aris to share a little bit on why DNS abuse topic is important for at large on AP Radio specifically in this case. With that, I end my talk, but I'll hand it back to Aris. Thank you.
Okay, thank you, Enchin, for that one. With regards to Pralo and at large, DNS abuse is really very important and a hot topic right now because of the fact that users are being affected with regards to this one. So it's not really more on the networking side or the technical side, but even users are being affected. And it's like users should also be able to know and to be aware of such things in a way so that they would be able to protect themselves in a way. So even some mitigations on a personal level, that would be very, very important. And also right now, with regards to at large, it is really on top of our outreach and engagement goals to spread the word in terms of what is really DNS abuse and how DNS abuse is really affecting not only the ones who are running the internet or running the networks, but also the ones who are being affected by it, more specifically the users per se. But as of this point, that would be one of the goals and one really on how this specific topic really affects the users per se. But anyway, to continue, I would be calling somebody who will be discussing about the ALS that is being who is partnering with Apralo in delivering some of the awareness here in our country. And for a while, I'll be calling on Winthrop to the floor. And before he comes here, I would be introducing him. So a consultant and a writer with the Philippine chapter of the Internet Society, where he is really mostly engaged on technical and policy issues with various stakeholders across both nationally and internationally. So he has been working on several internet-related issues for over a decade now. Sorry to say, Win, and was formerly a senior vice president for advocacies with the Philippine Internet Commerce Society. He is also an editor of PC Magazine Philippines. So I would like to welcome to the floor Mr. Winthrop Yu, the chair of ISOC PH.
Okay, thank you, Aris. Welcome, Yanqing, Champika, and all our other friends here. Lito Avaria of PH Cert, Save Nakaboke from Fiji. And I'm particularly glad to be here at this hotel today because the Internet Society's Philippine chapter was rejuvenated in this very same hotel, also at an African conference exactly 14 years ago, February 24, 2009. So we've been around for 14 years. And at the time, we met people, for example, Aris, the original people from the Philippine chapter. Some of you will have met Bayani Benjamin Lara, who's now with PHNOG. He's still an ISOC Philippine chapter officer, as is Achi Atienza. And at the time, we met with the Asia Pacific Bureau, the newly formed Asia Pacific Bureau of the Internet Society, who happened to be the immediate past chairman and the founding chairman of Apralo. Raj Singh is somewhere in the conference, and he's a compatriot of Save. So I'm very happy to be here. Now, fast forward to today. You all have your experiences with the COVID pandemic in your own countries. And might call it the silver lining for this is we find, especially here in the Philippines, that the uptake and the usage of the internet has grown tremendously. In the Philippines, for the Philippines as an example, whereas a lot of people previously would only post, let's say, food porn photos to Instagram. Because of the pandemic, they were now forced to work from home, to do distance learning, and that really stressed the infrastructure. Fortunately, the Philippines was able to up its connectivity quality just before the pandemic. But you will also notice that in certain respects, there's also a negative side to increased consumption of internet connectivity. And that is mainly that a lot of people who were not too involved or not using the internet too much before, we're now using more of the internet and we're subject to, for example, scams, malware, and they were not prepared to deal with this. So there's a lot of awareness and capacity building that we all have to do in our respective countries to bring all the relatively new internet users up to speed. So we're really happy with resources. For example, both ICANN, ISOC, many of the iStar orgs have learning platforms, and we should encourage our citizens, our fellow internet users in our countries to take advantage of these learning resources. And also quite timely, I believe before the pandemic, ICANN had already started a DNS abuse. They were already considering the issue. So this has now come to fruition, and I will let Champika speak to that. Thank you. And again, welcome to the Philippines.
Thank you again, Win, for introducing ISOC PH to our audiences here today. So to get into the main focus for today's session, I would like to call on somebody who is quite familiar to you and who is an expert to the field. And I would like to introduce him. And our expert is the Regional Technical Engagement Manager for APAC at ICANN. And he represents ICANN in technical, security, law enforcement, and capacity building forums, primarily in the APAC region. So prior to ICANN, he held managerial, specialist, and liaison roles at APNIC, the Regional Internet Registry, which is a PIR, for APAC. So he started his career with IBM as a technical specialist and has worked in the IT industry, academia, research, and training environments. So he holds a postgraduate degree in computer science and engineering, as well as a professional education qualifications in cybersecurity. So he also serves in various technical community groups and committees. So for our expert for today's session, may I call on Mr. Champika Wijayatunga.
Yeah, thank you, Aris, for that long introduction. And also, actually, I want to welcome all of you for this session. Very happy to know you all. So this session, the objective, of course, now we discussed, it's all about the DNS abuse. So we would also actually call this DNS security threats. It's pretty much, the same thing. So the whole idea is that, maybe I might control the slides. For us to understand that there are lots of security threats in DNS. Now, in a simple form, if you consider that, because DNS is something that we use every day, every time, right? Even without knowingly, when we browse, when we access our mobile apps, when we send emails and so on, we use DNS all the time behind the scenes. Now, also, if you consider about your organizational, say, if you have domain name in your organization, you have several resources related to that. You could be running your mail servers, you could be running your DNS servers, you could be running some database servers, all that, right? So DNS is a public-facing infrastructure. So this is why it can get abused, right? So this is also why actually it is very important for us to secure our DNS infrastructure. Now, especially given that today's forum is Apricot, and also I'm assuming that most of the people who are attending here, they are operational people. So I wanted to actually focus a bit more onto the operational aspects. And that's why I thought I'll discuss more on the operational aspects. So now simply, if you consider how the DNS you can see that the client, right? So we carry all these devices with us, phones and laptops and things like that. So the queries would go from our devices to the recursive resolvers. So these recursive resolvers are managed by like ISPs, mobile operators, and and also actually the mobile operators, and also actually the sometimes the corporates as well. So they operate these recursive resolvers. So these queries would go into these recursive resolvers, and then from recursive resolvers, it goes on to various servers called authoritative servers. So these authoritative servers, again, DNS is a hierarchical namespace, and then we have root servers on the top, and then we have top-level domain servers, next level or the second level domain servers, and so on. So in your organizations, you could be managing some of these servers as well, especially if you are ISP, if you are a network operator, if you are a mobile operator, most likely you could be managing recursive resolvers for your clients. But if you are a corporate, say you are a university, say you are a bank, and so on, you could be managing these authoritative servers as well. So basically, you will have to answer queries for various DNS related questions. So this is where the things can go wrong, and some queries can get abused as well. So this is where we have to think from DNS abuse, especially from an operational perspective. Now, the problem in DNS is that when you ask a question from a certain server, you might get a response, but we don't know really this response is coming from the right party, right? This response could be coming from basically someone who is not supposed to be running that particular server. So there is always this possibility of evil responses coming from, say, unknown server, right? So this is where the issue is. And this is why actually a lot of abuses do happen in the DNS space. Say, for example, you are supposed to talk to me, but someone else is talking on behalf of myself, right? So this is why these kind of abuses can happen. So one of the very important thing in DNS, what we have to consider is the authenticity of the responses. So if you ask any question from a server, we have to make sure that that response really coming from the right party who is supposed to respond. So this is authenticity. And the other thing is the integrity. Integrity means if I respond to you with a certain response, whether that response is not modified in the middle, because someone else can get this response and change it to something else and provide that answer to the client. So if you have your device, you send a query to your recursive resolver, could be your ISP, could be your mobile operator, and then if the mobile operator is not doing any sort of validation whether this response is correct, that can be abused, right? So there can be various ways that the DNS can be abused. So that's why we have quite a lot of threats and abuses that we find today. And also the other thing is that DNS attack space is too large because it's a big ecosystem. It's not just one party who is handling all this DNS related infrastructure. So we find that there are users, clients, then we see that the recursive resolve operators, ISPs, mobile operators, and so on. Then we have the authoritative name server operators. We have root server operators. We have TLD server operators. We have second level operators. So there are lots of parties. Then we have registries, registrars, resellers, registrants. So there are many parties involved in this whole DNS ecosystem. So things can go wrong in so many different places. So the DNS ecosystem is so complex, and even if one party is not doing their job rightly, the DNS has an ecosystem that can get abused, right? So that's why if we have to make sure that we do the right thing, all those parties, different players in the whole DNS ecosystem, they have to do their right part. I mean, they have to do their part right correctly, right? So that's the essence of that. And also the other thing what we have to understand is DNS has been there for 40 plus years. DNS protocol was originally, the first RFCs were written back in early 1980s. So more than 40 years ago, right? So that's a long time ago. So since then, of course, during that time, during early 80s, security was not a big priority. So even in the original protocol itself, there was not much of emphasis given to the security aspects. But then later on, many of the security features were implemented. There were many RFCs were written. So there are so many updates, so many new security mechanisms has come over the last 40 years. So we cannot just rely on the original DNS protocol itself. We have to have all these other updates, best practices to make sure that DNS is secure now, right? So that's also something that we have to consider. So that's why I was telling you before, DNS data integrity is very important. The authenticity is very important. So we have to actually consider these important things, and to make sure that there are mechanisms, there are security mechanisms that we have implemented to protect these appropriate areas in the DNS, right? We also have lots of these namespace risks that we encounter. For example, if you see this example.com versus that example.com, you will see one of the character has an accent. But if you see these two names in a small device, say in your mobile phone, sometimes you might just see those two are same. But in actual fact, it's not same, because if you take the actual domain name, one is in ASCII, the Latin characters, example.com. And then this one, if you convert that to the ASCII, it converts into a different domain name. So if some party who gets this domain name and display that as example.com in this way, easily the user can get misled. Because nowadays there are these internationalized domain names as well, where you can have domain names not only in English, not only in Latin characters, but also in other different scripts. It's always possible that the users can get confused quite a lot, and they can think that we are going to this website, but instead they're going into a wrong website, or kind of similar looking domain name, but it's actually a different website, maybe run by an attacker, for example. So in these ways, DNS can be abused as well. And then even when we type, right, our, fat fingers, when we write example.com, we might make a mistake. We actually don't write it properly. And then we go into another website, another domain. And then someone who want to really abuse DNS, they can buy that domain name, and then they can have a similar looking website. And then the user can get still misled, and then they might provide their credentials. It could be a bank website, it could be a social media site. So they might give their credentials into that. So these are, various different ways that the DNS can be abused. Redirections can happen. Redirections means you tend to go to a certain server, but then the queries can be redirect to a different server. So these are possibilities. Resolvers getting hijacked. earlier I showed you how the DNS queries get resolved. We think that our queries are going into our ISP's DNS servers, or we think that our queries are going into our mobile operator servers. But then these queries can be hijacked by an attacker, and then our queries can go into attacker servers. So these are also abuses. Say, for example, this can be done through malware. Sometimes if you visit a malware infected site, malware might get downloaded into your device, and then the malware might change your DNS server settings, because in your device, in your laptop, in your mobile phone and so on, you have DNS servers configured. So all your queries by default go into your ISP or your mobile operator. But then if those things are changed by the malware, then your queries go into a different place, right? So those kind of things can happen. That's what we call resolver hijackings. So that's a DNS abuse as well. Denial of services. That means if you're offering some service, this can be denied, and these are called denial of service or simply DDoS type attacks. Hierarchical namespace, because DNS is a very hierarchical namespace. And then if you abuse the top levels, then the rest of the domains underneath yourself can also be abused. So if you have example.com, and if example.com is abused, then things below example.com, say something.example.com, can also be abused as well. So there are many abuses can happen in the DNS space. Registrant compromises. How many of you have your own domain names here? How many of you have? Yeah, so if you have your own domain names, you are given a certain portal access by your registrar, right? So if your credentials are being captured by an attacker, right, through one of those methods that I was telling you before, things like cache poisoning, things like resolver hijackings and things like that. If your credentials are being hijacked, then the attacker can get into your portal and change your DNS settings. So they may change your DNS servers. They may change your mail servers, right? All those things can be changed. And then if you don't have proper protection, they may even change the registrar. Say if you have got the domain from a certain registrar, they may change the registrar as well, right? So this is also why you have to have some things like registrar locks, registry locks, and so on, so that you may not, the attackers may not be able to change those information, even if they get into your portal access or account and so on, right? So we may have to consider all those. If the registrar is compromised, the damage is even more, right? If the registrant is compromised, at least, they might be able to change the things related to your DNS account. But if the registrar is compromised, or if there are some loopholes in the system, if there are some vulnerabilities and so on, if they can compromise the registrar, the damage is much more, because each registrar has got much more domains under their control. If the registry is compromised, the things are even much more worse, right? Because you're talking about a whole registry system, right? So when you go above the, because DNS is a hierarchical space, and when you go along top of these, hierarchical space, of course, the risk is much, much more. So if you are managing a registry, you have to emphasize quite a lot on the security, the abuse side of it. If you are still managing a registrar, it is also important that you spend a lot of emphasis on the security. Even if you are a registrant, you still have to have some emphasis on the security aspects. There are vulnerabilities related to DNS software as well, right? So if you are using some certain DNS softwares, it is very important that you pay attention to that, because there can be vulnerabilities. So this is also why if you manage multiple DNS name servers, it is always a good practice that you have some variety. You don't have the same DNS server across all your name servers. You change it, right? You have some different name servers. In that way, you can avoid these DNS abuses. Okay. So DNSSEC, in fact, actually, before we came here, there was some session going on DNSSEC as well. If you were in this class, in that session who were listening to DNSSEC, you may have understood why DNSSEC is important. DNSSEC protects your DNS data. So if there are some certain abuses that can happen from data side of it, you can protect that by implementing DNSSEC. Okay, so now there are some recommendations depending on who you are. If you are a registry, if you are a registrar, if you are a DNS operator, and so on, try to offer DNSSEC services to your clients, or kind of your stakeholders, basically, right? So this is very important. And also, they would recognize that as well. Say, for example, me, if I want to pick an ISP, I would always go for ISP who can offer DNSSEC service, so that I know that I can protect myself. If I have some domain names, if I want to sign my domain name, I would want to go to a DNS service provider who can help me with that. So if you can help that, then you have some better opportunity even to get to get more customers and so on, right? So this is something, especially if you are a DNS operator, you can think of providing DNSSEC as a service. If you are a company, if you are a corporate, if you are a financial institution and so on, try to sign your domain name as well. That's important. Because all these abusers, attackers, and so on, they would target financial institutions, right? They would target corporates. So that's why, especially for corporates, financial institutions, and so on, DNSSEC is something that you should always consider. If you are ISP, you are providing resolver service to your customers. If you are providing resolver service to your customers, enable DNSSEC, right? It's not a difficult thing. You can always enable DNSSEC very easily. If you are from government, if you are a policymaker, try to have some proper guidelines to your institutions in your country, right? If you are from the government, maybe the government institutions, they can consider DNSSEC at least for government-related domains, right? So the governments can come up with these kind of mandates as well, the guidelines, policies, and so on. If you are a user, ask from your ISPs, can you provide me DNSSEC service? Can you enable DNSSEC in your resolvers so that I can actually I can safely visit these websites and so on? More the user demand comes from, then the ISPs would decide, mobile operators would decide whether they should, enable DNSSEC or not. So in general, having some awareness about DNSSEC is always beneficial, right? Especially to handle DNS abuse. Now, from ICANN side, I also actually want to talk about a couple of projects that we are doing. I mean, there are many activities happening in relation to DNS abuse, but given that this forum is more of a operational forum, Apricot is operational forum, I want to highlight these two projects. One of these is called Domain Abuse Activity Reporting, or simply we call it as DAR. So DAR project, the whole objective of this is to focus on certain type of DNS abuses. Because ICANN has got contracted parties, all these top-level domains, the generic top-level domains, they share their zone file with ICANN. So we can actually have a look at those zone files and see what type of abusive domains can be there within those domains or those zones. And then we can create some reportings so that community can learn from this. And also those registries, they can look into those abusers and correct themselves as well, right? So that's the whole idea. So we are looking at around 1,000 plus top-level domains, which can contain about more than 200 million top-level domains, more than 200 million second-level domains, right? So those kind of figures we are talking about. And also we are looking at very specific abuses like spam, botnet command and controls, phishing, malware distributions. So these are some very specific areas, very specific abuses that we are looking in this DAR project, right? And also actually, we actually, there are some reputation block list actually. So we are getting some feeds from these block lists as well. So based on all those feeds, we come up with a score, right? And then we can actually have some proper evaluation, right? Now, I want to share some of these statistics so that you can get some idea about it. So if you really look at, I mean, this is like last month's report, January 2023. So based on that, these are the breakdowns of domains identified with security threats across all these DAR threat types like spam, botnet command and controls, phishing, and so on. So you can see that in the legacy GTLDs, legacy ones like .coms, .net, edu, and so on. Those are the historical ones. I mean, still exist, of course, but they are still legacy ones. But if you consider new generic top-level domains, these are like the new ones since after like, in more recent times, the new ones, right? Because there are thousands of new ones as well. So you can still see spam is the most dominant abuse what we see. Because all those attackers, they try to send all those malware lists and all those things through spam. That's where, when you get all these spams, that's only people click links and so on, right? So you still see a lot of spam domains. There are malware domains, certain percentage. There are a lot of phishing domains as well, fair bit, right? Botnet command and controls. So you can have some sort of comparison with the legacy domains as well as new GTLDs. These reports are available every month, right, through ICANN. If you go to ICANN website and even you can search DAR project, these kind of reports are available every month. So you can go through, if you want more details, you can go through and find more information. I just want to give you some idea, actually, especially from abuse point of view, what info is available. This is, some further breakdowns in terms of domains. So you can, this is like in relation to number of domains related to these abuses. Right? Again, you'll see lot of spam domains in comparison to malware, phishing, botnets, and so on. Okay, and this is again legacy versus new GTLDs. Okay, now before I actually wind up with another project, now this, remember, I also told you before that these are based on generic top-level domain stats. Now, from recent times, this project was also open to country code top-level domains. So if any of you here is an operator of a country code top-level domain like .ph, for example, or .sg, or all these country code top-level domains, they can also join this DAR project. So if they share their zone file with ICANN, ICANN can share this kind of information with the registry, that appropriate registry as well. So they can actually then go into more details and take actions. So currently, I think around 21 country code top-level domains worldwide, they share their zone files with ICANN. In the Asia Pacific region, we have 5 country code top-level domains. They share their zone files with ICANN. So they get these kind of more detailed information so that they can take actions. So even if there is some CCTLD here who are willing to share your zone file with ICANN, you can get this kind of information so that you can take actions, right? But anyway, these are from generic top-level domains point of view, right? Not CCTLDs. Question?
Yeah. Hi, myself Gaurav Kansal. So basically, before DAR, the same project was in the name of, I think, Centralized Zone Data Services, CZDNS.
Yes.
Something similar. So from that time onwards, I think from last 2.5 years, we were consuming the GTLD zone files. Why we were consuming is we are always under phishing domain attacks. I am from an organization which handles the government websites. So everyone wants to have a phishing page of mine. So what we think of, we cannot do anything. So what we think of was, if we can have a domain files, at least I will block those domains in my network or because my organization uses my recursive DNS. Plus, I can ask my through the centralized intelligence agencies, I can get that domain at least blocked in my country. So unfortunately, this time I am able to talk to you directly. From last 2 years, I am thinking, what is stopping ICANN to get the files from .ccTLD also? Because nowadays, if I have 1144 GTLDs, but I have 200 CCTLDs. So suppose, as because we are in Philippines, I'm giving you an example. My website is gauravconsole.in, and if a phishing guy hosts on gauravconsole.in.ph, I cannot figure out. I have other ways, but that are more typical in nature. So I must be sure that CCTLD must not have shared this willingly. You must have forced them to do it. Otherwise, we cannot have in a go. So all CGTLDs coming on board that, yeah, I'm ready. So please, humble request to force CCTLDs to do this. This will help community, at least for the ones who are facing a cyber fraud attack heavily. At least my country, because of the after this in the current leadership under the Honorable Prime Minister, we are moving for digital India. So everything in India, even for buying a cigarette, I can pay through online without any charges. So now cyber attack is increasing day and day. Every day I get a 2 message from a bank that your account is getting blocked. Get it KYC, do the KYC update, and the domain is Bank of India .ccTLD. I don't have any option. So ICANN has the powers. Use humble request, use the power, Do it by a carrot approach or by stick. Do it. Bring on the CCTLDs on this. Point number 2. I was seeing the DAR reports, I think 1 year back. So you say, you just give me the charts. This is beautiful for a board of director guys. For guys like technical, working hands-on in nature, why don't you share these number of domains which are malicious in nature? Just give me the domains. I will get rid of them out of my country, which I can do. Within my country, I can block those domains, but you are just giving me these charts, beautiful charts. But for me, I appreciate it. I am not criticizing anyone, but at least this is my personal view, not my organization view. Is of no use to me. So if you can give me a domain, which you can easily give, just give it. I will consume it over API, integrate it to my DNS. Completely will at least save my country. And this everyone can do.
Okay.
Philippines can do for Philippines. I can do for India. And we will always be obliged to ICANN to save us.
Okay. Okay, let me come back to your, before I get back to your 2 points. Now, first of all, you have to understand that ICANN is not a police, ICANN is not a regulator, right? So,
I think by carrot or stick, you bring the GTLD on a day one.
Yeah. So let me, express the ICANN perspective, right? So ICANN is not, as I said, ICANN is not police, ICANN is not regulator, and so on. So ICANN is a community-based organization, and it is up to the community to come up with the policies and so on, so that it can consider whether that is doable or not, right? So in the first place. Now coming to the points that you raised, the first point. We still have that CZDS, right? So if you want to have some further access and so on, so there is a process for that. You can access, you can request for that, and then go with that. These statistics are now again. You were mentioning about the domains, right? Specific domains. Yeah. Now this one, again, we don't publish in these DAR reports and so on. We don't publish the exact domains, right? Because there are, of course, reasons behind that, right? But of course, if the appropriate registry, if they want to take actions and so on, appropriate registry, they can get this information. They can get the specific stuff. So this is also why we are telling, even if some CCTLD voluntary joins this, say for example, if you're from .in India, .in has joined this. .in has joined the DAR project. So they can get very specific information. So it is up to them to act on that, right?
Can .in get the all complete list of domains, malicious domains?
Yeah, they do get it, because they get that they have joined this project, so they can get much more information. No, because if you're from IN, that's a separate story, but outside world, that's not the case, right? So it's up to the registry to act on that. And also you mentioned a point about, okay, why not I can force all the CCTLD registries to join in this. But again, CCTLD registries are not contracted parties, right? GTLDs are contracted parties of ICANN, but CCTLDs are not ICANN contracted parties. So that is also why, there's no way, there's nothing called forcing, okay?
I agree.
Yeah. Sorry, Champiga, but due to the interest of time, we're just going to get one more. Then after that one, we're going to wrap up the session.
Yeah.
Yes, please.
Hello, I'm Mike. I work in Cambodia. We do have the issue that you addressed previously. You're encouraging people to have DNSSEC. The Cambodian regulator does not enable DNSSEC, so we can't actually do anything. Now that I hear this conversation, what does ICANN has as an ability to actually tell the CCTLD to enable DNSSEC Is there any pull or forward? Because you're saying you're not the police, but I was managing the .kh domain at 2001, and then ICANN told me it must be transferred to the government. So you had the power to transfer it, but you don't have the power to make them to do a good job. Thank you.
Oh, just to add a question on his one, if I can we have a policy through CCNSO to get it done?
I mean, of course, the CCNSO is a forum that CCTLDs can have some discussion there, right? And
Can we force through CCNSO to have to all join, or can we not?
so again, as I said, ICANN does not have any contracts as such, right? But if you are a GTLD, in the contract itself, DNSSEC deployment, they have to do. That is why 100%, GTLDs, 100% they have deployed. But whatever the remaining 10%, if you take the whole TLD as a generalized thing, 90% of the TLDs they have deployed, but that 10% comes from CCTLDs, just like Cambodia is one of them. Yes. I mean, ICANN is also not, we are not just staying like this. We have been having some dialogues with many of these countries who has not deployed DNSSEC. So we are trying our best as well. We are trying to have some dialogue, provide the support, provide the training.
Just a follow-up. Let me just put the urgency on this. Yeah, the national banking regulator and the national exchange regulator both have made regulations that require banks and brokers to have a .kh domain name, but they don't have DNSSEC. So we're actually making the security worse in the country by forcing people to use a top-level domain that is not secured.
Yeah.
There is some sense of urgency here that we get this conversation going.
Yeah. Yeah. So ICANN has been also talking to many of these countries who has not deployed DNSSEC. Right. So it's not that just we are sitting, without doing anything. So even for Cambodia, we do that. And we are in the process. I mean, we have provided some training courses. We have tried to engage them and so on. But end of the day, it's up to them whether, they want to deploy or not. Right. Maybe it is a possibility that they may not be having enough resources within their organization. That could be a possibility. Yeah. So, but if you think that even you can facilitate, right, them to have some capacity building sessions and so on, we are quite happy to actually work with you and the CCTLD and so on and provide this necessary capacity building. Yes.
Thank you, Champika. Sorry to cut you off, but our ALS chair is insisting, so I'll be giving him just a short chance to relay something, and after that, we're going to close the session.
Yeah.
And I'll be kind, Champika.
Please.
I feel for you. I understand the problems with the CC.
No, these are all practical issues. Yeah.
I was with a redelegation effort 20 years ago for .ph. Didn't work, but I was part of that. And it's good you asked the question about DNSSEC because Aris himself, he's a dean of a school, and he was asking if he could implement DNSSEC in his school. I said no, because that's hierarchical. Precisely. If .ph is not implementing DNSSEC, then who do you refer to? Who's the authoritative? You have to have it from the top down. So it has to be .ph. On the other hand, I have an idea. It's a good thing you mentioned banks. It's important. The DNSSEC is important for banks, to prevent man-in-the-middle spoofing, things like that, right? Somebody remind me. Let me talk to Achi and Bani. These are the PHNOG people, right? So they're with the ISPs. Now, what I propose to do, we scare the banks. We tell them you're doing everything security-wise, but your URLs are basically insecure. Why? Because you cannot implement DNSSEC. Why can't we implement DNSSEC? Because Joel Dicini doesn't want to implement DNSSEC, the .ph holder. And if we do this from a bottom-up sort of thing, from the stakeholders who are most affected by the security issues brought about by DNSSEC, then they will be the ones to pressure both the Philippine government and the CCTLD manager to implement it. It's worth a try. Thank you for the idea about banks. So that's one way of going about it. Okay.
Yeah.
And I was going to ask also Champika, because the first question of mine was about DNSSEC, so that's already been answered. My second one, these DAR reports, is there another series of reports, including a newsletter or magazine related to DNS abuse being put out by ICANN?
Yeah, I mean, there are a number of projects. Of course, due to the limited time, we didn't want to go into all those projects and so on. But DAR project is specifically on the DNS abuse, on these specific areas, botnet phishing attacks, and then spam and malware, right? So we publish this monthly. So if you want to actually look into those monthly reports, I mean, these are only a couple of graphs I took from that, but then these reports are much more detailed. If you can get much more details.
Yes, in fact, when you mentioned that, for example, you used the example of .in.
Yeah.
Since they're part of the DAR project, then they get the details, right?
Yes.
So I was already discussing with Aris.
I mean, they can get the details about the .in, for example.
About that
Yeah.
only.
So if .ph joins it, .ph can get the
about that.
reports about .ph abuse.
Not about .in.
No, not about .in.
Okay, that's too bad. Aris and I were planning to buy a new GDLT, so we could access all the data, Anyway, forget it.
Yeah. Yeah.
Okay, thank you, Champika.
Okay.
Okay, thank you. Champika, thank you so much for gracing.
Yeah,
our
and if you have,
Yes.
feel free to, we'll be around this week. So if you have more questions,
Yes, if
we
you
can
have more
some more
questions.
dialogue, more questions, Q&A and so on. And by the way, my colleague Save is also sitting there. So feel free to, yeah, he's a long-standing ICANNer. So feel free to talk to him as well.
Involved right now, Sabi.
Yeah. And, so we are here, Jenshin, myself, Save, and we also have another colleague from ICANN as well. So feel free to talk to us, and we are quite happy to help you.
So thank you so much, Champika. And we are 15 minutes beyond our time, but I hope that you were able to, get a lot of information. And if you still have any more concerns or questions, we are here during the week, just like what Champika had mentioned, and you could approach him anytime. He's a very amicable one. So again, I would be closing this session. And again, thank you so much, everyone, for attending. We do appreciate you being here. So
Thank you.
session is adjourned. Thank you.
Yeah. Thank you, Aris.